For our final orientation control, we will look at perpendicularity, which means something is exactly 90 degrees to some datum. In this part, they are controlling perpendicularity of that surface. You can also control, as in the bottom picture, perpendicularity of the center plane of a flat thing, or perpendicularity of the center axis of a round thing. Here it is applied to a surface, and that means the tolerance zone is two parallel planes. Here they are. Here's perpendicularity applied to an axis of a round thing. That means the tolerance zone is a cylinder. Here's perpendicularity applied to a flat thing. That means the tolerance zone is two parallel planes. And I would just point out that this control, notice, is opposite a dimension line. So that means this is controlling the feature of size, not some surface. So that's how we know we're talking about the center plane of the feature of size. Perpendicularity on a surface is the thing you see the most often. Here is ASME talking about applying it to a surface of a, let's say, an angle iron. And they have applied the feature control frame to an extension line off of the surface, which means this is a surface control. Here is perpendicularity applied to the center axis of a round pin. Now that tolerance is applied to the dimension, the size dimension relative to that axis. Here is ASME. These are both out of the ASME standard. Here's ASME applying perpendicularity to the axis of a hole, and here is the tolerance zone. Here is ASME applying perpendicularity to the axis of a pin or a shaft, and here is the cylindrical tolerance zone. Here is ASME applying perpendicularity to the center plane of a slot. And how do we know it's the center plane? Because they have stuck that feature control frame onto the size dimension, not onto the surface. And so what they are telling us is they are controlling the center plane of that flat feature. It would look like this. There's the tolerance zone, two parallel planes. When you put perpendicularity on a feature of size, there's always a material condition implied in there. Oftentimes we put an M in our feature control frame to say, this is the tolerance if you make the part at MMC. If you don't say anything, then it's implied that the material condition is regardless of feature size. Whatever size you make the part, here's the tolerance. This guy here has a tolerance that applies at maximum material condition. So that told the inspector that they could use a fixed size hole in their gauge to check these parts. And now they'll just drop those hubs down into that gauge hole and see if they work or not. If they go into the hole, it's a good part. Here's ASME talking about the perpendicularity tolerance on a pin and the tolerance zone, and the inspector figuring out the virtual condition to make the gauge tool. You can think about how when you put perpendicularity on a surface, you are indirectly controlling flatness. So if you just put this perpendicular within two parallel planes that are 12 thousandths apart relative to datum A, you are saying not only does that surface have to be perpendicular, but by implication, all the bumps on that surface have to be flat within 12 thousandths, don't they? What this is saying is there are two parallel planes 12 thousandths apart. Well, maybe what you mean is It's okay to be out of square by 12 thousandths, but wherever it sits, you really need that surface to be flat within 4 thousandths. So if that's what you need, then you can use two controls. You can say you want the surface to be perpendicular within 12 thousandths, and you want it to be flat within 4 thousandths. Or if you're doing a tolerance on a pin, let's say a shaft, you want it to be perpendicular within a cylindrical tolerance zone that has a diameter of 15 thousandths, but wherever that lands, you also need it to be pretty straight. You need the straightness of the axis to land within a tolerance zone that's 5 thousandths in diameter. So here you see the two tolerance zones, the big one and the small one, nested together. Remember how angle dimensions are always basic? Basic dimensions and geometric tolerances travel in pairs. So with an angular tolerance, you tell them, here's the theoretically exact basic angle dimension, and here's the tolerance. Well, perpendicularity dimensions are basic too. They're an implied basic 90. If you think back to a couple of weeks ago when we were talking about basic dimensions, we mentioned a fundamental dimensioning rule in the ASME standard. Actually, we mentioned two of them. There's one dimensioning rule that we looked at a year ago that says if it looks like 90, it is 90. Recently, a couple of weeks ago, we looked at the next rule, which said if your features are dimensioned with basic dimensions, those boxes there, then the angles are 90-degree basic dimensions. And here is that rule, Rule 10. If they're located by basic dimensions, the angles are a basic 90. So I just say that to clear up the fact that, let me back up, to clear up the fact that when we do angles, the angle dimensions are always basic. If you have something that's not 90 degrees, you give an angle dimension with a box around it. If you have something that is 90 degrees, you just locate the features and put a box around each dimension. Okay, inspecting perpendicularity. Well, here's the not very efficient way of doing it. You could, if you needed to, put your part on a surface plate and then get a precision square, snug the part up against the precision square, and then get a series of gauge wires, here's a gauge wire, and see if they'll fit in that gap or not. It's a little bit like using feeler gauges to check, I don't know if you've ever checked spark plug gaps or distributor points with feeler gauges, little thin strips of metal. That's what this is like. Here is ASME talking about using one datum to check the perpendicularity of this angle iron, and how it's better if you use two datums. And this is related to something we looked at when we talked about checking a part with a sign bar, how if you only give the inspector one datum, they're not allowed to square up this part. They just have to squiggle it around on the thing that they're resting surface A on. And what they will have to do is keep trying, rotate the part a little bit, check it with an indicator, rotate it a little bit more, check it with an indicator, until they find the very lowest dial indicator reading. Well, that's rather time consuming. If you give them two datums, then they can snug the part up against a flat surface and a linear surface, 3 points of contact and 2 points of contact, and now they have a solid surface to measure against. You will often see in an inspection shop a surface plate, which is a granite thing, And then a precision square, this drawing here is likely a precision square that's made out of granite. So you will see granite things that look like this sort of truncated trapezoid thing. If they are made out of metal, they're more likely to be an L-shaped. If they're made out of granite, they're more likely to be this wedge shape. And now here is our inspector inspecting the surface that is supposed to be perpendicular within two parallel planes that are 5 thousandths apart for this part.